Right. Hello again. So I would like to have a talk concerning segmentation of solar coronal structures and solar flare forecasting for SDO images. And I'm going to resume a bit to the part where we want to evaluate these algorithms to have the possibility in the future to have them on board on a future spacecraft. So as Vicky said earlier, when we design such algorithms, we always have to have this possibility in our mind, not only when we have the final model, but also during designing these models. First of all, why such algorithm would be actually interesting to have it on board? We have in our mind several use cases. First of all, in the case of solar orbiter, we know that we have several telescopes. One of them is capturing the full disk, and another one is having a high resolution images, but in a less wide field of view. So one has to carefully design advanced the mission scenario where the high resolution telescope will capture interesting topics, interesting areas of the sun, and not miss interesting areas that could be potentially interesting to downlink the ground. So in such a case, we could have the full disk telescope capturing images, then segment active region coronal holes, for example. And as soon as we have an interesting area, then we actually can then trigger to function the high resolution imager and then point it to that interesting area. So at the same point, we can actually save power and also prioritize images to send to the Earth. So overall, we can actually optimize the downlink information that we send to the Earth, and we have the possibility to prioritize and disregard samples. So first, we need to build such algorithms, and we need a lot of data. And thankfully, we can use the SDO machine learning ready dataset from Galvez collaborators. So we have access to multiple wavelengths of AIA with a cadence of 6 minutes and for at least 10 years. And even though we don't have the big 4K by 4K resolution, 512 by 512 is more than enough for our purpose. So for our case, we're going to concentrate on wavelengths of 171 and 193, but one in the future can also incorporate other wavelengths. So to our original study, we concentrate to pre-propose the SCSnet. We have Simon here had proposed this some years ago. And they propose a DUNet architecture, which is a bit heavy architecture, has 70 million parameters, but at the same time is very accurate. So there are two proposed models, one for active region segmentation and one for coronal hole, like here in the illustration. And with a nice chronological data split, it has been evaluated really accurately with dice current intersection over union. At the same time, since we want to have an alternative of a smaller network, we use the same data set. We convert it to a detection problem. So instead of accurate masks, now we have boundary boxes. But again, for our purpose, this is enough. We kept the same data split in order to be able to compare with SCSnet. And then again, we made our two models, one of active region and one for coronal holes. And at the same time, we proposed another alternative, a non-data-driven one. It uses basic computer vision operation, so we have the acronym BCPO. So first, we're doing automatic thresholding based on ORTSU method, and specifically here we're using multiple ORTSU in order to detect to accurately segment the active regions and then the coronal holes. Then, in order to have less noisy results, we run morphological filtering, which again we can run it automatically. And in order to get these different colors, as you see here, we also trained an unsupervised scheme where we can distinguish, mainly based on the area, we can distinguish bright points with coronal holes, and sometimes we can also distinguish filaments with coronal holes, but this is again a work in progress. So first, we wanted to compare these three architectures of how feasible it is to port them on board. And directly we see that it's a bit optimistic to have such a huge UNet with 78 million parameters. To have it, it's optimistic to have it embedded to FPGA and to have low power requirements and characteristics. Whereas YOLO, it is something that can be considered since it has 95% less parameters. But again, there is the drawback that we have some connections that they are going from one layer to another, so we have to retain some information. So I got some feedback from Pedro about that. So again, this means that some data has to be retained, then we have to communicate with peripherals, and this again means that we are going to have increased power consumption. At the same time, we have this PCVO algorithm that possibly it's not very easily to parallelize. So it's not recommended to have it at FPGA, but we still have it in our mind because it can be really accurate. It can be not data driven, and it can generate data in order to better fine tune SDSSnet and YOLO. Here is architecture in detail. So as I said, SDSSnet is a UNet. YOLO is the most straightforward, and in the end we have the output of the coordinates of the boxes, and then what the class and the probability of being this class. And here we see the flow of the BCVO. We have the multiple O2, and then we have for the high intensity values and for the low intensity values, we have morphological filtering and then the final segmentation masks. And from both SDSSnet and BCVO, we can use this characterization scheme where we can extract some features, and then we can do clustering either using k-means, either using PSNE, and we can actually characterize our findings. So if we want to compare them based on the accuracy, we can use the intersection over union metric, which is defined like here, this schematic. And as I said, we have the active region models and the coronal hole models. And always the first column corresponds to SDSSnet. The second one is the YOLO version 8 nano model. And the third one is the BCVO. As expected, at first we see that SDSSnet is on both cases more accurate. But if we see a bit critically the results, we have to reconsider our choice, because actually here we are evaluating intersection over union over masks in these two cases, and here we have boundary boxes. So in order to have a fair comparison, we convert the segmentation problem into detection problem. So for SDSSnet and BCVO in both cases, we convert the inputs and outputs and the ground truths into boundary boxes. And then we can see that the difference in the end with YOLO is very small, and actually YOLO can be a bit more accurate. And we think this comes to the fact that YOLO has been designed to perform such a general detection. So it means that YOLO is a good compromise in terms of characteristics, but also can offer satisfactory performance for our scientific goal. And then we went the next step, as Vicky said earlier. We have to consider that if we want to have such an algorithm run to the spacecraft autonomously, we have to have a better picture of what's going to be the data that actually the model will run. Because normally we train our model to level 2 data, meaning highly preprocessed, very well calibrated, and compatible for machine learning tools. But it's not the case if we have raw data It's not the case if we want to have an algorithm that takes this raw data, and with minimum processing, we want to have our models compatible to the machine learning model. So we managed to get some collaborations, some level 0 SDO data, and we tried to try our models without any fine tuning. So first we realized that we have to do some pre-processing. With very, very minimal pre-processing, we saw that we don't have some serious artifacts, only the fact that we have 4 acquisitions, so there is some discontinuity between the quadrants, which can be negligible for the active region models, but can affect the performance of coronal hole models. So we experimented with as light as possible pre-processing schemes, and then we realized that if we calculate the overall mean image, and then per quadrant again calculate the mean. So first get the mean and overall subtract from this quadrant, and then add the mean of each quadrant. We can have this kind of image, which, as you can see, it's really close to us level 2 data. And this actually was the case. And when we evaluated on this pre-processed data, but again, not fully calibrated like level 2, so it's, let's say, pre-processed level 0, we got very similar results like we had before. Again, we are comparing detection with detection and not segmentation with detection. And here, if we inspect some examples using SESNet, we can verify what I stated before, that the active region segmentation models can tolerate this discontinuity, so we can actually overlay the findings and we can map to the active region very well. And here we have a coronal hole, and the coronal hole model, even if we have this discontinuity, again, the model can detect very well. So these images have, you see that we have still this discontinuities, meaning that the models can actually be compatible with very, very, very limited pre-processing, because we have to keep in mind that this pre-processing, again, will run in the spacecraft, and we cannot have a very, very heavy process. So overall, we tried 3 frameworks for segmentation and detection of coronal structures, mainly active region and coronal holes. In the future, we would like to include filaments, but we're looking for such a data set that will be unbiased and to be high quality. We want to explore also, so now we were using YOLO version 8 nano, which has 3.2 million parameters. There is a YOLO version 11 nano with 2.8 million parameters, but it's not only the parameters that it matters, but also the network topology. And generally, we want to investigate even larger architectures. And we hope that one of these variants will be tested either to soft GPU setting that we had this presentation earlier by Gianluca, or to try one FPGA from KTH like Pedro proposed earlier. And generally, we can explore how this characterization scheme can further improve our segmentation findings. Thank you very much.
Questions? I'd like to ask if you tried also how stable is the segmentation for this level 0 data. So for example, if you took like 20 images in a row and to see if the model was able to successfully segment the structures in the consecutive images.
So for level 0, we managed to acquire 2 subsets. So some thing I remember it was 15 days, 1 image per day every midnight for December of 2024, and then almost a full month 2025. I think again it was December. So these numbers it's analysis if it's a mean values of all these images. So with all these images, we treat it as test set by doing this pre-processing. So as you can see, it really looks very close at level 2. So if we do a bit minimum pre-processing, a bit lighter, then we see it's not very accurate, especially the coronal model. And indeed, here all these numbers we are doing for specific for SSNet, we have the probability map, the output, and with threshold of 0.5. Of course, if we look into deeper and we try to validate a bit, we can play with this, but then it's not very fair. So we try to have a universal setting. And then we have, of course, Roman work where he managed to reprocess a bit further the images, and then we have a bit better findings. But again, it remains to be seen if this is fair for all the images or for a specific subset.
Yeah. On the last slide, I mean, yeah. Also, I noticed it before. So why on the panel C you have the edges you are not, which are not masked?
Yeah, so this is on poorly preprocessed, just to illustrate that the active region models can actually tolerate these discontinuities. So these are the examples on poorly preprocessed. And of course, it has this and even better performance if we fully preprocess the images. So these are a bit more challenging examples to illustrate that the algorithm can actually tolerate these small artifacts and still can have very promising results.
Yeah.
But these are in cases that it works.
But you have a very bright regions which are still out, which is not, I would not say small artifact.
The limb here.
Here, yeah, it's in the limb, right?
No. I mean, in general, the masks are having edges which are out. They look almost like they are shifted for some reason.
Yeah, but as you can see, it's not perfect. We still.
Yeah.
So so you can understand that the best would be to be close to 0.8, 0 to 1. So the coronal is going to between 0.6 to 7, and this because we don't get the perfect score. And also you have to imagine that we evaluate on SPOCA masks, which also are not perfect because they are conservative coronal active regions as well. So indeed, if we make ourselves the annotations, the score will be different.
Yeah.
And this is actually very interesting to have a small test set where we can have more careful masks, and then we can have a bit more unbiased. Or I'm aiming to validate my works in this benchmark dataset, the 29 images of SDO, like Simon did present earlier, which will be interesting. Which already we have the SSNet score in there. This, so I can actually try the BCVO algorithm to see where it score.
I would wonder if it would have a time series which are like one images after another, how much, if you would be estimating how much of the edges of the coronal holes is out. So maybe systematically, if there is a certain level,
yeah, that's interesting,
a certain percentage of it, so then you can actually account for it because you have then. You can do it on the poorly pre-processed, which means you are going towards the level 0 data.
Mm-hmm.
That would be interesting.
I know for the active region model, it works even for very, very poorly. But for if so, you see this one is, let's say, in the medium. So I have tested here. If I go here, I had a result where it was only here and it was finding many coronal holes. So specifically the coronal hole model works better for this kind of situations. For this one, it will just, it's like seeing only one quadrant and then very poorly.
Because anyway, it's difficult for
it's challenging. Yeah.
Are there any other questions? Also, we can check online if there are any questions.
It's quite late after.
It's quite late, and we have one more talk left. But yes, very interesting. Thank you.